Right, let's get started. Good morning, everyone. Welcome back. We are in the penultimate week of the program. Very exciting, and I hope you're having a lot of fun in the program and also working on your projects. And today's talk, we are going to talk about more about quantum-inspired algorithms, in particular, quantum-inspired algorithms for computational fluid dynamics. Turbulence is one of the most complex and fascinating phenomena in classical physics. It appears everywhere from weather systems to aircraft design. And in this session, we are going to talk more about this. We are going to talk about a novel approach to analyzing and simulating turbulent flows using quantum-inspired algorithms. And for this, we have with us Dr. Juan Jose Mendoza Arenas from the University of Pittsburgh. Juan is an assistant professor in the Department of Mechanical Engineering and Material Science at the University of Pittsburgh, and he's also an associate assistant professor in the Department of Physics and Astronomy. And he obtained his BSc and MSc at the Universidad. Okay, I should have practiced that before. Sorry, I don't think I can pronounce the name of your university right. Juan, so
No problem.
apologies for that.
No problem.
And he went on to receive his PhD in physics at the University of Oxford. And then he joined Pittsburgh and University of Pittsburgh in 2023. And we're very excited to welcome him to the program. Welcome, Juan, and over to you.
Thank you very much for the kind introduction. I'm very happy to be here and very excited to share some of our recent work. So now let me share the screen. Do you see my screen?
Yeah.
Okay, perfect. So thank you very much for giving me the opportunity to present some of our recent outcomes. And as Anaya was saying, our recent work is focused on using quantum-inspired algorithms for solving problems in fluid dynamics. First, I'd like to acknowledge the collaboration of our several colleagues, in particular for the colleagues that are located at the University of Pittsburgh. We have 3 PhD students that have been working on the calculations, Bobby Pinkston, Hirada Lipana, and Felipe Gomez. And we have also strong collaboration with Professors Juni Liu and Payman Gibi. Also, I'd like to acknowledge external collaborators, Dita Yaksh, Haider Salman, and Nick Gurianov, in Europe, and Brian McDermott, Feng Shan, and Zhongxin Zhao here in the US. This is the outline of my presentation. First, I'd like to introduce the main concept that we are going to apply for simulating different types of problems in fluid dynamics, which is the concept of matrix product state. This concept was originally created for dealing with the problems in many-body quantum physics, but because of its success, it was then taken to other fields of science and engineering, and now it is being applied for solving partial differential equations. In this sense, people refer to this concept as quantum-inspired. So I'd like to start explaining a little bit how we can build matrix product states, how we can apply them, and then I'll show some of the results when we perform these applications. I'm going to focus on applications to 2 types of problems, classical and quantum fluids. In the classical case, I'm going to focus on compressible reacting flows. And in the case of quantum, I'm going to focus on Bose-Einstein condensates. And finally, I'd like to discuss the summary and some perspectives for future work. So let me explain first the need of this type of techniques in the field of materials, condensed matter. This is actually the field where I come from. I was initially working several years ago in understanding properties of materials, for example, magnetism, superconductivity, topological phases. And initially, again, for dealing with this type of problems, is that matrix product states were conceived, and that's where they have shined for several years. So why would we need this type of technique for dealing with problems in condensed matter? Then I'll show how we can translate this to other fields. As I said, we might be interested in the area of material science in understanding different types of properties, conducting properties of charge, of energy, topological properties, etc. And one way to approach this type of problem is by considering models and idealizations of our materials, where we try to capture the basic ingredients that might explain these different properties. So, for example, you have heard about the Howard model, the Heisenberg model for studying order of charge, order of spin, etc. In these simplifications, you consider something like this. Let's say that you want to study the 2-dimensional properties of a material, so you propose a model like the one that is shown in this figure. You say, well, okay, maybe my particles, which are going to be electrons with spin up or down, can jump only to neighboring sites in my lattice. If they are on the same side of the lattice, they interact with each other through Coulomb repulsion. So with this type of scheme, you introduce your model. This actually corresponds to the Howard model. And it is indeed a very strong simplification. Real materials are not just like this. But even though these models are quite simple, dealing with them is very, very challenging. So why is that? Let's say that we want to understand the properties of a lattice of n sites. We have, for example, one particle per site. So we would like to solve time evolution. So we need to obtain a solution for time-dependent Schrödinger equation. So we establish our Hamiltonian built from these processes on our model, and we obtain the time evolution of our state. In general, we can write the state of our system in this form as a linear combination of all the basis elements in my system, where here n sub j denotes all the possible basis elements for site j in my lattice. The dimension of the Hilbert space of site j is here called lowercase d. So for example, if we consider one of these sites in my lattice for spinfold fermions, we have that d is equals to 4. We can have on a site that it can be empty, it can have a spin down, it can have spin up, or it can have a spin down and up. So d equals to 4. We have this linear combination of d to the power of n basis elements. So we need to specify d to the power of n coefficient. This is a problem that grows exponentially. Because of that, well, it is quite challenging. If we wanted to solve this equation exactly in a computer using, well, exact diagonalization, well, that is not going to work for large systems because very soon you're going to run out of memory. You could also try to do some analytical calculation. Many people have obtained very nice results about that, but in many cases, getting analytical solutions away from perturbative limits is extremely difficult. In some cases, that might not even be possible. There are many other methods that people have invented to deal with this exponential complexity. And matrix Proc states corresponds to one of these most powerful methods in some special situations, in one-dimensional systems, short-range interactions, but well, their success actually goes beyond. So let me describe, well, what a matrix Proc state is and why it would be useful. For this, I'm going to resort to a very common way to introduce tensors, which is through a this diagrammatic representation, where we represent tensors as some shape, and if the tensor is of order n, then we have n legs coming out of it. So here are some basic examples of this representation of tensors. If we have a scalar, for example, a tensor of order 0, it is just a shape. I chose here a circle. If we have a vector, so a tensor of order 1, we have a shape and one leg coming out of it. The leg corresponds to this index I of my vector. Similarly for a matrix, this is a tensor of order 2, so we have two legs coming out of the shape corresponding to the two indices ij of my matrix. Similarly for three-dimensional matrices, and so on and so forth. The object of our interest now is a tensor of order n, like this one, a shape and n legs coming out of it, which precisely corresponds to this type of object, right? This coefficient, this collection of coefficients corresponds to a tensor of order n. Again, exponentially large object. The idea of matrix Proc states is to approximate this exponentially large tensor by a collection of tensors of low order, so order 2 at the boundaries, order 3 in the bulk. So we can use tensors of a small size to get the most important information of the original exponentially large tensor. We are going to assign to each tensor, for example, a letter A. So here, A n sub 1 corresponds to the tensor of site 1, A sub n2, the tensor of site 2, etc., etc. When we have here two tensors being connected, we indicate that those are being contracted. We are multiplying those tensors. The advantages of this representation are that, well, on the one hand, as I'm going to explain in a moment, we can control the size of these tensors so they can be actually quite small, allowing us to get a vast compression in memory. Because of that, we can perform efficient calculations using these tensors, and we don't have to use the whole tensor. If we want to do some time evolution or some optimization, we can do that tensor by tensor, and this leads to very good algorithms for different purposes. Let me explain now how can we build in principle a matrix Proc state, how we demonstrate that such an object exists. This is the standard way that you can find in different reviews. Let's consider here a tensor of order n, again my shape with n legs coming out of it, and let's do the following. Let's take the first leg, let's separate this leg from the rest, and let's consider that leg as a row. Let's combine the other n minus 1 legs and think of them as column. So we have a matrix. Let's perform singular value decomposition on that matrix. So we have now, as a result, the product of three matrices, U, S and V dagger, just as indicated here. We multiply S and V dagger, so now we get this structure, and now we do something similar. We combine these two legs, think of them as a row. We combine these other n minus 2 legs, we think of them as column, do singular value decomposition, and again we get something like U, S, V dagger. And we again multiply S with V dagger, we repeat the process until we reach this type of a structure. This is the famous matrix product state. You will see that when we do the singular value compositions, here we get matrices U's. Those matrices U's can be reshaped into tensors, again of order 3 in the bulk, order 2 at the boundaries, and here I show explicitly, well, the indices of these tensors. The indices that go down correspond to the physical indices, and these horizontal indices correspond to all the connection between the different tensors. Here, again, I show the product of the different tensors of all the sides, and here I show, well, this product, but in an open way, explicitly writing the contraction of the different horizontal indices. So now this is going to be the object of our interest. How does it work? We think of a system of many interacting particles. Let's imagine a one-dimensional lattice of spins, for example. We associate to each site in my lattice a tensor. This tensor is going to have the information associated to that site. And by connecting tensors with their neighbors, we establish correlations across the system. So now the wave function is represented by this object. So we no longer have here the exponentially large tensor, but we have here this product of tensors. Now, if you don't do any approximation during this process, if you just do this and keep all the matrices exactly, you don't really gain anything. You can show by construction that the size of these tensors grow exponentially as we go toward the center of the lattice. So for this representation to be useful, we have to do some approximation. And the approximation is kind of natural. When we do here the singular value composition and assume that the singular values are ordered from larger to smaller, we can take with the largest singular value compositions, the largest singular values. And it is common in the literature to refer to these largest singular values that we maintain with the letter chi. So instead of having a very large number of singular values, we stick to chi of them. Now, instead of having a number of parameters here that grows exponentially with n, we have a number of parameters that increases linearly with n. So the size of each tensor is approximately d times chi squared. So we achieve exponential compression. This is, well, the point of using matrix product states. This concept has been extended to 2 dimensions. There are other types of networks that people have used. Those are a bit more complex. I'm going to very briefly mention something about them towards the end of my talk. But okay, I have shown you that the MPS structure can be built, but I still haven't explained why would this be useful. The key word here is locality. So why can we approximate the state just keeping chi singular values and still getting good results? Because of locality. If we consider a one-dimensional system of interacting particles, for example, where the interactions remain at short range and there is no gap, well, people have shown that the system satisfies the so-called area law when you are away from critical points, when you are away from quantum phase transitions. So for this area law, we have that the entanglement between two subsystems of my system, like the two subsystems I'm showing here with the cursor, the entanglement between those two subsystems depends on the boundary between the two subsystems. In one dimension, the boundary between the two subsystems that I indicated is a point. So no matter how big I make my lattice, the boundary is still a point. Entanglement is going to saturate with the system size. Again, if you are away from critical points. If you are located at critical point, so a quantum phase transition, you violate the area law, but this violation is just logarithmic in the system size. So it's not a very strong violation of the area law. So overall, in one-dimensional systems with short-range interactions with a gap, we have that entanglement remains, well, localized in space essentially. That is the notion of locality. Because of that, we can truncate our matrices of singular values here in the SVDs, take only chi singular values and still get a good representation, accurate results with a very little error. We as the users, we can control the value of chi. So we say how many singular values do we want. Of course, the larger number of singular values that we keep, the better our calculation is going to be, but it's also going to be, well, more expensive computationally. Again, by dealing with individual tensors, we can perform efficient manipulation for dealing with different types of calculations. And at the end of my talk, I'm going to mention that also MPS and other types of networks provide a road towards quantum computing. I'd like to briefly mention here and that, well, being a person that comes from condensed matter, some of my work still is in this area. So here I highlight some of our work, some of them recent, some of them of a few years ago, but I think those are quite nice. For example, some of the research that we do in my group corresponds to studying transport of energy, of particles, essentially studying quantum transport in different situations. In this recent paper, we studied the implementation or the theoretical development of a concept of a quantum diode. We have also studied controlling degrees of freedom of matter using light. Also, we have studied properties of cold atoms in optical lattices, well, using tensor networks. So, for example, for studying insulating phases, superfluid phases, well, etc. So, this is part of the work that we do in my research group. But this talk is going to focus on applications for solving partial differential equations, which I found fascinating. To me, I think it was very nice to see that there was this technique that was very powerful for dealing with problems in condensed matter, and now this technique is ported to a completely different area. I found it really fascinating. So for this different area for solving differential equations, this is essentially how it works. I'm going to skip technical details. Of course, if you're interested, you can let me know. You can send me an email. I can provide more information. I'm going to keep here, well, the idea like in a broad sense for the sake of clarity. First of all, let me explain why could we use matrix-Proof state structures for dealing with functions. So how can we encode a function into a matrix-Proof state? Well, let's consider, for simplicity here, a function defined over x, so one dimension, let's say with this range in space. One way in which you could solve a differential equation of f is to discretize your derivatives. So you select a bunch of grid points. You transform your differential equation to a matrix equation, and you solve this equation by obtaining the functions evaluated at those grid points. Let's suppose we want to encode our function in n qubits. So we would have 2 to the power of n grid points. One way in which we would select those 2 to the power of n grid points would be like this. We just define them in this form. So those grid points would be 0, 1 divided by 2 to the power of n, 2 divided by 2 to the power of n, etc. Let's represent the same grid points, but in a slightly different way. So by binary encoding, essentially. I'm going to show here an example for 4 qubits, so 16 grid points, indicated here by these points of colors in the x-axis. Let's consider first our first qubit n sub 1. We are going to do the following process. Let's stand up in some point in x. If we are standing up in a point that is in the first half, then n sub 1 is assigned the value of 0. If we are standing up in the second half, then n sub 1 has the value 1. Now let's go for the second qubit. Let's suppose we are in the first half. If in this first half we are in the first quarter, the second qubit we are going to assign to n2 the value of 0. If we are in the second half, in the second quarter, we assign to n2 the value of 1. Something similar if we are on the second half. If we are in the third quarter, we assign to n2 the value of 0. If we are in the fourth quarter, we assign to n2 the value of 1. And so on and so forth for the other values of L3 and 4 and j, etc. So we see that in this way, we assign to each grid point a unique combination of zeros and ones, which can be written in this form. So n sub 1 tells me the information about the largest length scale that I'm resolving, so half of the system. N sub 2 tells me the information about the second biggest length scale that I'm resolving, so the quarters, and so on and so forth. If I write my grid points like this, and I evaluate a function in these grid points, then I can write a function in this form as a tensor of order n. So in this way, we can write the function as the same object that we are using for building a matrix-Proof state representation. So we in principle could take this tensor, use a sequence of singular value decompositions, and build our matrix-Proof state. So that is the way in which you could use this approach for encoding information. Now, why would that be of any use? This is also one of the key questions. In principle, you could take any tensor of order n, put it in matrix-Proof state form, but that doesn't mean that's going to be of any use. There has to be a reason why you can use an approximate representation with little error. So let's discuss this reason for the particular case of the simulation of turbulent flows. Oh, excuse me 1 second. All right. This application of turbulent flows was first discussed in this paper by some of the colleagues that I mentioned in one of my first slides, by Nick Gurianov, who was the first author. This paper also includes Dite Yaksh, Peyman Gibi, Hesam Babai, who was the speaker, I think 1 week ago. And the idea was the following. Well, first of all, it is important to mention the following. Maybe you have heard this already from several speakers, but it is also good to reinforce it. The simulation of turbulence is extremely challenging. If you want to analyze very accurately a turbulent flow, well, you'll have to face a very complex computational problem. There are several reasons why you will face this problem. Well, one, of course, is characterized by the Reynolds number. The Reynolds number is a dimensional number that gives you the information about the nature of your flow. It incorporates information about viscosity, the velocity of the flow, the geometry. But overall, let's say for simplicity, that you will increase the Reynolds number if the velocity of your flow increases. Again, that also depends on geometry, on viscosity, but I think it might be easier to picture it like that. The number of grid points that you would need to take to accurately resolve a flow of certain Reynolds number is given by this law, which is a very strong increase with the Reynolds number, and 9 divided by 4. So that is one way to picture it. Another way to picture it is the following. If we want to have an accurate calculation of a turbulent flow, for example, here I'm showing a flame, you need to resolve all the relevant length scales from the largest length scale, which is going to be of this essentially the size of your system, to the smallest length scale, which would be, for example, the Kolmogorov length scale, the length scale with energy dissipated. So that could go from several meters to a few millimeters or tens of millimeters. So that's a vast range of length scale that you have to resolve. And you will see here that if you want to resolve a length scale divided by 2, you have to add, let's say, another index. So you could see already that resolving accurately these types of objects, this type of quantities, well, the velocity of a turbulent flow, the density, the temperature, well, whatever transport variable you're interested in, that requires an exponential complexity. If you have a system of dimension capital D, then to resolve n length scales on each direction, you need due to the power of dn grid points. So this is, again, an exponential complexity. So you can see this is a problem of very different nature to that of many quantum physics, but still you find here a problem that has a complexity that increases exponentially. There are several reviews, books that also illustrate how hard it is to solve turbulent flows by an example of daily life. So it is common for these books to say, if you want to accurately resolve the flow of air around the wing of an airplane at standard flight conditions, you'll have to perform a calculation for several thousands of years. And actually, that is very similar to an argument that you have heard for sure several times regarding the need of quantum computing for solving problems in condensed matter. Quantum computers might provide this path to deal with problems that have this exponential complexity that might take thousands of years to be solved in our best classical computers. Well, here you might also want to use such an approach, but well, here we're not really talking about quantum computing. We have a classical approach to try to deal with this exponential complexity. So how does this work? We have to build a matrix-Proof state in a way similar to what I discussed before. Here I illustrate this in a two-dimensional lattice. So let's suppose that we are going to study a flow in 2 dimensions. We want to obtain different transport variables, again, components of velocity, density, temperature, reacting scalars, well, whatever is involved in your problem. And for doing the construction of an MPS, one way to do it is to divide your spatial range into 2 subgrids. One coarse grid, here represented by the red dots, and a finer subgrid, here represented by the blue squares attached to each red dot. So we take our transport variable of interest, we reshape it as a matrix where a coarse grid corresponds to row, the finer subgrid corresponds to column. You do singular value decomposition, and you get for your transport variable this decomposition. Sum over, well, the product of the corresponding singular values, a function of the coarse grid, and a function of the finer subgrid. So essentially, this would correspond to U, this could correspond to the V dagger when we do the singular value composition that I showed before. We can truncate the singular value composition, so we only take chi singular values, and then we repeat the process for this function f of the final subgrid until we reach the final length scale that we resolve, and in this way we build our matrix Proust state. So again, we can build this structure, but why would this be of any use? The key reason, the physical reason why using this type of structure would be useful is again a concept of locality. In this situation, the concept of locality comes from the mechanism of energy cascade. In three-dimensional systems, turbulent systems, energy goes from the largest length scales to the smallest length scales in this cascade mechanism, where eddies of certain size interact with eddies of similar size. And through this interaction, energy is moved from the large to the small. So here we have, again, a notion of locality, not in the sense of many of the quantum systems, here a notion of locality in the length scales of the interacting eddies. And you see that we build our MPS so that each index corresponds to a different resolved length scale. So this object that we have created here would be naturally adequate for encapsulating this locality in the sense of length scales. This insight well demonstrated in this paper by Nick Gurianov and other colleagues, where they showed results for two-dimensional and three-dimensional flows. They compare the results of exact calculations with the, in fluid dynamics, those are called DNS, direct numerical simulation. And they perform calculations of tensor networks, matrix Proust states, in particular matrix Proust states, with some truncation parameter. And for 2 dimensions and 3 dimensions, the results agree very well in a way that the results of the MPS require around 10% of the degrees of freedom that are required for the DNS. So you can get a very significant advantage in memory using a lot of, much less memory. This year, some of the same authors published another work, this time simulating Fokker-Planck equation using a technique called large eddy simulation in the context of this LES approach. And for this calculation, they obtained compressions of memory of the order of 10 to the power of 5. So we can see that indeed this technique is very promising for dealing with these exponentially large objects. Now, let me illustrate with a simple example how does it work before showing more complex results. Let me illustrate it with a testbed equation that incorporates a nonlinearity, which is Berger's equation. Here we have a term of advection, here we have diffusion, and in this case, here we find the nonlinearity, where U corresponds to the speed of propagation. There are different ways in which you could solve this using MPS. I'm going to show one of the approaches with forward Euler implementation. Instead of forward Euler, you could do something else, maybe Runge-Kutta or some other method, but this is for the sake of illustration. So it would work like this. First, you encode your transport variable of interest, in this case U, into an MPS, here represented by this Dirac notation. Also, here we have these derivatives acting on our state. We act on our state and we get another state. These derivatives will correspond to operators, which in the language of matrix Proust states can be built in the so-called matrix Proust operators, or MPOs. I'm not going to give details on how you build MPOs for derivative operators. In some of our papers that are coming out in the following weeks, we explain this in detail. You can also let me know if you have interest on how you do this. I can provide those details, but for the moment, just believe me that there is an efficient way to create a matrix Proust representation for operators as well. So we have an MPO for derivative operators. We specify our bond dimension chi or truncation parameter. Those are the names that chi usually receives. And for the time evolution, we do a loop. So we evolve time step after time step, where at each time step, we calculate the special derivatives by applying the derivative operators on our MPS. Then we calculate the time derivative doing this operation, adding the results of the diffusion and advection. Here I should mention that for the nonlinearity, we have to use a concept which is the Hadamard product. This is element-wise multiplication. This is an expensive operation, and there is research on how to do this calculation in MPS, reducing the complexity. Again, I'm not going to give details about this. If you want more information, I can let you know. Well, after calculating the time derivative, you update your variable and you keep doing the loop until reaching the time of interest. Let's see here the results for the solution of Berger's equation, where we have this initial Gaussian profile. The expectation here is that as time passes, this is going to move to the right, so this is the effect of advection. But because of this nonlinearity, we have a difference in the speed of propagation. At the bottom part, u is small, so the bottom part is propagating very slowly. At the top part, u is large, so it moves faster. And in this way, you develop this shock, and MPS captures well this shock. Here we show the error comparing the MPS solution for different values of chi to DNS. And we observe that as we increase chi, the error is decreasing. Already for chi equals 4, you have a very good solution of your equation using around 22% of the parameters that would be required for DNS. That's not that much of a compression, but this is just a one-dimensional system. You can see much larger compressions in systems of higher dimension. After that introduction and showing you well, the logic of why this technique would work, let me apply it now to our case of interest, complex classical flows and well, quantum fluids. The first application is that of compressible and reacting flows. In this case, we are going to use the metric-Stokes states to solve Navier-Stokes equations, considering also the possibility of chemical reactions of some reacting species. So here we have to deal with a very complex set of equations, which you see here. Well, we have tons of terms. The overall idea is that we are going to evolve in time the following situation. We have two types of reacting species, C1 and C2. C1 corresponds to this stream that goes to the right. C2 corresponds to the stream that goes to the left. Initially, we create an instability between the two streams. So because of this instability, the two streams start mixing. So a shear layer is formed. The idea is to optimize well, this mixing, as this leads to the formation of the product of the chemical reaction, which is the species C3. This is going to be a two-dimensional problem, so our velocity components are u and v. We are going to first assess whether the MPS captures the correct solution, and then we are going to evaluate the effects of compressibility and exothermicity. So essentially the effects of the Mach number and of chemical reactions. It is important to mention that we have implemented these algorithms using iTensor. This is one of the most famous libraries that are available for tensor networks in general, including with matrix-Stokes states. This is very convenient, and again, it is very nice for me to see that iTensor, like all the other libraries for matrix-Stokes states and tensor networks, those were initially developed for dealing with problems of many quantum systems. But now we can take advantage of the machinery that was created well in these libraries to solve problems of very different nature. First, let's take a case without chemical reactions and observe that the MPS results agree with those of DNS. These are the different parameters of our simulation, the Reynolds number, Mach number. These parameters here, Dam-Kohler number and heat release parameter, those are the parameters associated to the chemical reactions, so we are going to turn them on a little bit later. For this calculation, we observe that MPS indeed captures very well the results of DNS for the different types of interest. Here, I'm showing the results for one well, the distribution of one of the reacting species, C1. We see a similar result for the vorticity of the system, where again, MPS is capturing very well the results of DNS. So this is for verifying that our implementation works very well. After verifying this, now let's focus only on MPS calculations, and let's see if these calculations can capture the expected physics when we vary Mach number, Dam-Kohler number, and heat release parameter. So let's evaluate first effect of compressibility. Again, Dam-Kohler number 0, heat release parameter 0, and we perform calculations for different Mach numbers. Mach number was the ratio of the velocity of our flow divided by the speed of sound. The expectation that people have when you vary the Mach number is the following. When you increase the Mach number, you reduce pressure fluctuations. And as a result, the growth of the shear layer is delayed, so the mixing is delayed. And that's precisely what we observe here. In this figure, we show well, the distribution of the first species, and the second figure we show vorticity. And those figures indeed show this effect. As we increase the Mach number, the mixing of the species is being delayed. We can quantify in different forms this mixing. On the figures on the right, for example, here on top, we are plotting the Reynolds shear stress, and here we have the y-axis, where in the x-axis we have done the average over x. And this is given by this product of these differences of the values of velocities minus their mean. And we see that for low Mach numbers, where essentially the flow behaves as incompressible, there is a large value of these stresses here around, well, the boundaries of the two streams. But as we increase the Mach number, so as we suppress the mixing, this is being strongly suppressed. We can also capture this effect with the vorticity thickness. The vorticity thickness is a measure of, well, of the thickness of the function of vorticity in the y-axis. And we see that as the Mach number increases, the vorticity thickness decreases, indicating that the growth of the shear layer is being delayed. So the effect of compressibility is captured correctly. Now let's consider the effect of exothermicity. In this situation, we are going to, well, fix the Mach number, have a fixed value of the Dampler number, and vary the heat release parameter, which is the rate of energy release per chemical reaction. And the overall expectation here is similar. And the effect of increasing the heat release parameter. As we increase the heat release parameter, so we release more heat, we increase the temperature in the system, which decreases the density, and as a result, the mixing is also delayed. This is precisely observed here as we increase the heat release parameter. Indeed, we increase the heat release parameter, temperature increases in the system, and the growth of the shear layer is decreased. Here, this is demonstrated by showing the product of the chemical reaction C3, and here again, the vorticity. So the calculations with MPS are capturing the correct physics. And now let's discuss a bit the advantage that we can get with MPS. Well, of course, this advantage is initially related to a compression of memory. This compression is going to be evidenced more and more as we consider more and more complex flows, as we increase, for example, the Reynolds number. Here we have results of DNS. Here I'm going to analyze DNS data. And you can see for DNS that as we increase the Reynolds number, well, the flow becomes more complex. We have finer structure that we need to resolve. So we need to consider, well, more indices in our tensor to resolve these additional length scales. Here we are going to observe more the benefits of using an MPS. In this figure, I show the value of chi that is required for certain value of error in our calculation. This error here is quantified by the infidelity. Here I take different transport variables, density, the two components of velocity, and one of the reacting species. And we see that as we increase the Reynolds number for having the same error in our calculation, we require a lower chi than that corresponds to the same number of parameters of DNS. That critical chi is indicated here by this gray line. For density, for the components of velocity, as you increase the Reynolds number, you don't really have to increase that much your value of chi. It essentially saturates. For the more complex C sub 1, as we increase the Reynolds number, we have to keep increasing the required bond dimension. It hasn't saturated for the values of Reynolds number we have considered. But still, this value of chi is almost 1 order of magnitude smaller than the maximal chi that would correspond to having actually DNS. So as we increase the Reynolds number, we indeed see that we can have much more memory compression. This figure illustrates focusing on the simplest and on the more complex transport variables of this problem. So the density and C sub 1. Here, DOF and P sub T, those correspond to two different ways to measure the advantage. I'm not going to go into details of those two. Those two overall will kind of approach each other for large Reynolds numbers. But the point is that K here represents the percentage of gain in memory, or well, the amount of gain in memory, essentially. So even for the most complex problem, so for the most complex transfer variable, we can reduce the required memory for large Reynolds numbers in more than 1 order of magnitude. And for the simplest transport variable, that can be decreased around 5 orders of magnitude. So we can indeed see that MPS provides a very powerful way to suppress the amount of memory that you need to get a good calculation. As a final way to demonstrate the power of MPS for classical flows, here I compare MPS and DNS for some specific flow, and we also compare it with under-resolved DNS. Under-resolved DNS is a DNS using the same number of degrees of freedom that we are using for MPS. And we see that while MPS agrees with DNS, the under-resolved DNS doesn't agree. It misses the properties of the flow. So MPS is indeed using in a smart way the degrees of freedom it has at its disposal for correctly representing the flow. All right, that was about the application to classical fluid. I think I'm running out of time, so I'm going to go a little bit quickly here. Now I'd like to show application to Bose-Einstein condensates. Maybe you have seen this very well-known picture of the first observation of Bose-Einstein condensate, which then led to a Nobel Prize in 2001. In Bose-Einstein condensates, well, you can have very interesting hydrodynamic properties. Under some circumstances, you might find some properties that resemble those of classical flows, but there is a key difference when you consider the hydrodynamics of Bose-Einstein condensate, and it's that your singularities, well, your excitations, sorry, correspond to singularities described by quantized circulation. This doesn't happen in classical flows. In classical flows, your circulation can have an arbitrary value. But in these quantum fluids, the circulation is quantized. You can have just specific values of this result when you are in a evaluating it around a vortex. Essentially, here the singularities correspond to these quantized vortices where you have a hole, so a very low value in density. This is shown here in this figure, where essentially, well, this red shadow represents a trapped Bose-Einstein condensate, and this red tube represents the hole that it's inside the condensate, corresponding well to this vortex. This figure represents well the projection in 2D, where the black dot represents the hole, and this is a projection in density when we integrate y and z degrees of freedom, and indeed we see here a hole in density. So these quantized vortices correspond to holes in density with quantized circulation around them. And we can find very nice manifestations of these singularities. For example, vortex line, when we extend those over one axis. These lines can form dipoles. So for example, here we have one rotating in one direction, the other one rotating in the other direction, and those two move forward as a pair. So this is a vortex dipole. We can have a ring, a line connected with itself, and we can have the more complex effect of quantum turbulence. So this is the representation of turbulence, the emergence of turbulence in a quantum fluid. A very challenging problem. It has the same exponential complexity of classical flows, and it would be very exciting to be able to simulate quantum turbulence in larger and larger systems. I'm not going to show results about quantum turbulence, but I'm going to show results about the other types of excitations, which are stepping stones to have to go to the final goal of simulating quantum turbulence. So I'm going to show the results very quickly. Here you are going to solve Gross-Pitagor's equation, which is a mean field equation very common for the physics of boson and condensates, also known in other contexts as the nonlinear Schrödinger equation. So this is my Gross-Pitagor's equation, where psi is the wave function of my condensate. Here we have kinetic term. This is the trapping potential, the interaction. So G is the interaction strength, and here the chemical potential. We are going to solve this non-dimensional representation of the equation, where we also introduce this dissipation, where gamma corresponds to the coupling of a condensate to a thermal bath, and it's going to suppress some noise that makes the picture a little bit more complicated. We are also going to use a matrix product representation to solve this equation, but this time we are going to use a different method to what we used before. We are going to use the so-called time-dependent variational principle, or TDVP. This method, in the context of matrix product states, was again developed for solving problems in many quantum physics. And we just put our equation in an MPO. We call the TDVP function of I tensor, and we perform our time evolution. So it is quite nice, again, that we can just call this function designed for something else and still be able to solve this equation. First, let me show the example of a vortex dipole in 2D. Well, here are some initial conditions for the dipole, so I'm not going to give details of that. The important thing here is to compare the time evolution of DNS and the TDVP. And here you see that we can obtain very well these dynamics of the vortex pair. The two vortices are moving forward, and so we are only using 7% of the memory of DNS. Again, this is a simple problem, but still we can achieve a very vast memory compression. Here we have the infidelity for different values of gamma. As we decrease gamma, the calculation is more complex. We require more, a larger value of chi, so that also leads to a lower infidelity, but still the infidelity is low enough so the calculation is correctly captured. Now let's check the vortex string, in this time in 3 dimensions. Here we have calculations for 3 values of gamma, 10 to the minus 2, 10 to the minus 3, and 0. And we see that we capture the expected behavior. Here we don't compare in the calculation with DNS. I mean, there's no space for showing the DNS in simulation, but at plain sight, they agree. If you have a very strong dissipation, that dissipation is going to make your ring disappear. So yeah, maybe you don't want to have such a large dissipation, but still you overall see the expected behavior, the ring moving forward. And here again, we have infidelity for different values of gamma, showing that the results are in agreement with DNS, so infidelity lower than 10 to the minus 4. Something more interesting, vortex reconnection. This is one of the key elements that takes place in turbulence. Essentially, when you have vortex lines that meet, the connection between those lines can change, the topology can change. This is something that we illustrate here in this first video. Initially, you had these two dipoles, one horizontal, one vertical, and when they meet, they change the connection. The lines now, these two are now connected. Now these two are connected, the same for the lateral lines. And this results also in the emission of a ring. So we have to capture the whole thing, well, the motion of the line, the motion of the ring, to have an accurate calculation. For this case, we don't have DNS because it's becoming very demanding. To capture this problem with this effect with DNS, well, you can do that with systems that are not that large, so that's not that much of a problem, but you need a very big system to capture correctly an additional effect. You see that after the connection happens, there are some oscillations here in the lines. Those oscillations are known as Kelvin waves. And we need a very large system to observe very well those Kelvin waves. So for this, we did calculations with 2 to the power of 11 points per direction. And here we see this effect of the Kelvin wave. You see more the oscillations, which results also in the emission of more rings as time passes. And we are observing the expected physics in this situation. So even though we don't compare with DNS, we can say that our calculations are correct. Importantly, we are using a minimal memory compared to that would be required by DNS. So just 0.0067%. So vast compression memory. As a final example, I'd like to show some initial calculations of 2D turbulence when we have initial random distribution of vortices. And for this, well, we compare DNS with TDVP. If you look at the details of the calculations for the times I'm showing, the dynamics is very well captured by TDVP. When two vortices find each other, they can collide, they can destroy each other. When this happens, sound waves are emitted. Those are the waves that you see as if you were dealing with water. That's kind of what it looks like. And this behavior is very well captured by TDVP. Here we are not having that much of a reduction of memory, but this is just a two-dimensional system. This is not such a big system. It is expected that for larger systems, we will get a much larger compression of memory. All right, so just to finish, I'd like to very briefly mention again that we have performed calculations of different problems in fluid mechanics, classical flows, quantum systems, using matrix product structures, and we have successfully recovered the expected physics. In the future, we would like to simulate more complex systems, in particular 3D turbulent flows. For example, the simulation of a flame in classical or simulating quantum turbulence in 3D in quantum. We would like also to investigate the effect of different types of networks. MPS is just the most famous member of the family of tensor networks, but there are other famous members. These are the so-called PEPs, projected entangled pair states, three tensor networks, MERA, multi-scale entanglement normalization ansatz, and these are, in principle, able to capture better longer range correlation than MPS, but those are harder to deal with. So this is also a problem that we are starting to investigate right now. And finally, this also opens the way to use matrix product states as a programming paradigm for quantum computing. Maybe you have seen figures like this before in the previous sessions or talks, where these types of tensor networks can be directly uploaded into quantum computers. You see, well, the tensor network that I'm showing here, 3 MERA MPS, they look very similar to operations that you do in quantum circuits. So one way to connect classical with quantum could be perform calculations in classical with MPS. When we reach the limit, we upload those matrix process structures to quantum computer, and then we continue time evolution. These two papers by Suchi and by Tini are recent papers that describe the state of the art of using quantum computer for simulating differential equations, well, in particular for application of fluid dynamics. I think this is a very nice area of research, and for sure there is a lot to be done. I finally highlight here one recent article of our research group. I didn't talk about this article today. This is a purely quantum computing application for solving a linear equation, but still this is one intermediate step for being able to solve much more complex flows in quantum computing devices. Well, with that, I finish. Thank you for your attention.
Yeah, thank you, Juan. That was very exciting, and yeah, you explained it so clearly. And it's kind of impressive that like you could, with just a fraction of the memory, you can just get the same accuracy as with DNS. It's very impressive. Thank you.
Yeah, thanks.
Yeah. Yeah, I have a few questions, and we also have questions from our participants. I'm going to kind of read them out to you. So the first question is from Sujal from India. His question is, in MPS, we convert each coefficient of substates into product of small order matrices. So the number of those matrices for each coefficient is equal to the number of qubits or the number of lattice sites.
Let me go back here to the, okay, here. If we build this matrix prostate, we have as many tensors as sites in our lattice. Each tensor here reduces a tensor of order 3. We can imagine that tensor of order 3 as a collection of matrices. So you are going to have lowercase d matrices for each tensor. If you are dealing with qubits, lowercase d is 2. So if you are having here an MPS with d equals 2, that means that per site you have this tensor of order 3, which corresponds to a collection of 2 matrices per site. But yes, overall you have as many tensors as sites in your lattice.
Thank you. Yeah, kind of another question from him. Why are we choosing SVD for the decomposition?
SVD is the most common one that people choose. You don't have to. One of the reasons why it's the most common one is that it is because it reveals the singular values. And you can actually see how these singular values decay. You can analyze those singular values. I didn't show results about that, but if you look, for example, at the paper of Nigurianov, in this paper, they analyze very nicely the singular values corresponding to this type of flows. You could also use QR decomposition. You could use polar decomposition. I think QR is also quite common, but that one doesn't reveal the singular value. So maybe that's a reason why people wouldn't choose it. But its efficiency is also a good point why people would choose it. Polar decomposition, when I saw that was used, was in the implementation of TPUs. As far as I remember, that was because there was no SVD implementation of TPUs back then. So well, that was a few years ago. But yes, you can choose other ways for the composition. But if you check reviews, articles, they are going to mention these other decompositions, but when they do this construction, very likely they are going to exemplify it with the SVD.
Yeah, I was wondering that too. So you can kind of use something like a rank revealing QR instead as a cheaper alternative.
Yeah.
Okay. We have another question from Gerardo. So conceptually, why is turbulence well described with a 1D ansatz like MPS? I guess the notion of dimension is different, but basically, why don't we need something more expensive like PETs?
We might, actually. These initial calculations, I think they were very successful, but if we want to squeeze even more, it is likely that we might resort to PEPs. And that is actually what we are investigating right now. Well, not with PEPs. Right now, we're investigating MERA. Because indeed, what we are observing is that for simulating very complex problems, our value of chi is growing a lot. So I should hear that you still get a significant advantage compared to DNS, but still it's quite expensive. So initially we used MPS because it is simpler. That is the reason. I mean, we have an argument to say, well, there is locality, so MPS is good for representing the turbulent flow. But initially, it is because it's simple. MPS is the tensor network that most people use initially. But given that the value of chi is still quite large, it is true that we feel it is important to investigate other networks. So hopefully, not very long in the future, at least we have some results, something more concrete, well, to say about MERA, which is the one we are dealing with right now. And regarding PEPs, actually, we have started some discussion with some collaborators that use PEPs for many with quantum systems, so that we learn how we can encode flows in PEPs and we can do the time evolution. So that is definitely something that we are looking forward, well, to do in the near future, well, hopefully in the following months.
Thank you. So follow-up question on that. So the chi being used here is the bond dimension, right?
Sorry,
And
uh,
is chi the bond dimension?
Chi.
Chi, sorry.
Yeah, that's the one dimension.
Yeah. And is there something analogous to area loss for fluid dynamics phenomena?
The closest to an area law is represented in this figure. That is actually also discussed in the paper of Nick Guryanov on 2022. And that was that, well, instead of increasing well, the system size, you increase the Reynolds number. Well, increasing the Reynolds number means that you have to resolve more length costs, so that also represents an increase in the system size. You see in parentheses, this is the Reynolds number. This is the number of qubits that you need to consider for that corresponding Reynolds number. So the equivalent, well, up to now, the equivalent of area law is observing that as you increase the Reynolds number, or well, increase the system size, the chi for achieving certain accuracy saturates with that Reynolds number or with that system size. That would be similar to these figures where you have entanglement as a function of system size or as a function of a system, and that this entanglement saturates when you increase the system size, and that it grows logarithmically when you're at a quantum critical point. This would be at least I think the closest picture of that has built so far, of observing how some quantity saturates as you make your system bigger. So yeah, I don't think that at the moment there has been a formal development, like an analytical treatment of such an equivalent of area law, but that's the discussion that so far exists in the literature.
Thank you. Maybe we have time for one like kind of broader question. So I do see like more and more of being the use of like tensor networks and developing such quantum inspired algorithms really kind of pushing the limit of what we can do classically. When I feel like I see a lot of such work also coming out in like the quantum chemistry world, like where the people are really pushing the boundary of what we can do classically. And it was really kind of impressive to see that we can like get closer to DNS kind of accuracy with, with the fraction of the memory with doing tensor networks. And in kind of in your opinion, like, in the CFD field, where do you see as the limit of like at what point do we need quantum algorithms running on quantum computers for what scale of problems or for what phenomena or at like what accuracy levels do we actually have to like move on into quantum algorithms?
Well, in the sense of fluid dynamics, I think definitely turbulence is the problem that might require it. Well, assuming well you had a quantum computer which is noise resilient and this ideal quantum computer that we would like to have, because that would provide a way to deal with the exponential complexity of having to resolve all these length scales. Of course, when you think about quantum computing for fluid dynamics, you have to face some challenges that you don't have for other situations, like how do you deal with the nonlinearities? That makes it a bit troublesome. How do you deal with the fact that you have to perform non-unitary operators? I mean, that's not such a big deal. People have proposed simple ways to get around it, but still that makes the problem a little bit more complex. But if you want to obtain this accurate resolution of resolving all the length scales and also time scales of very complex flows, that's where the quantum computing approach could be very relevant in the near future. Even using tensor networks, even if you go beyond MPS and use PEPs or MERA, it might happen that there will be a very complex situation that still is very hard to deal with at the classical level. So for example, our reacting flow that we have here, if you consider a more realistic problem where you might have at least 11, 12 reacting species, In many cases, people use more than 30. In some other situations, maybe you need even more. So you have all these reacting species if you're dealing with a three-dimensional problem. So you have an extremely complex situation that might be very tough to deal with also with these techniques. And also you have to resolve very small time scales because chemical reactions correspond to very, very fast processes. So in those cases, maybe if you do tensor networks, you might find that rapidly you reach a bond dimension chi that leads to very slow calculations. In that case, then you could consider moving that information towards a quantum computer. So I don't think that is going to happen like very, very soon. I mean, we still need to have much better quantum devices, but well, many people are heavily working on that. But I think that is the type of problem that needs this type of machinery. And that motivated a lot some of our colleagues here at the University of Pittsburgh. So, for example, these professors that I mentioned at the beginning, Peyman Gibi, Junior Liu, Dita Yaksh, these colleagues think about how we can solve these very complex problems using quantum computing. And in fact, with UNU, we have been investigating another approach, different type of technique to use quantum computing for the purpose of dealing with the highly nonlinear equations, because that is also part of the problem. Not only the nonlinearity, but the fact that it might be very, very nonlinear. Like the nonlinearity could be huge. And once we have very powerful noise resilient quantum computers, maybe we can find ways to deal with that. But I think that is the prospect that is moving many of us right now for the near future.
Yeah, thank you. Yeah, I think algorithmically also we don't really have good ways of dealing with strong nonlinearity yet in terms of
Ye-
quantum. Yeah.
Yes, that's right. The most famous method is Carleman linearization. There have been many works that deal with Carleman. But even though that is expected to work beyond the theoretical calculation that they did initially, still they might. I think now people don't think that it's going to go that far in terms of nonlinearity. Another technique that we are investigating is well, it described a little bit in this review by Felix Tini, which is the so-called quantum nonlinear processing unit. That was actually discussed by Michael Lubach, who I think was also a speaker not long ago here.
Yeah, yeah.
We have discussed with him also several times about different things that we can do while using, for example, quantum devices. That mechanism for dealing with nonlinearities, I think, is also very exciting, but it has not been investigated that much. So I think right now people don't really know that much the limits of this concept of the quantum nonlinear processing units. Part of that is what we are doing now, with these colleagues that I mentioned initially from Ames Lab. We are starting to use these techniques for solving nonlinear equations, but still at the quantum simulator level. Hopefully, in the following months, we will see how that works for the actual quantum computer, evaluating different values for the nonlinearity. So then we can start having an idea on maybe how this works.
Yeah, thank you. That was really insightful, and it's kind of nice to see it all kind of come together. That some of the concepts that we discussed earlier in the program and tying it together with the real application work. It's really nice.
Yeah.
Thank you once again for taking the time to come and share your exciting work with us. I learned a lot, and I'm sure participants enjoyed it a lot too. And like we already have comments coming in on Discord that it was a very clear and interesting talk. And it was like it's fascinating for the participants also to see how the changes in algorithms, used in quantum computing are really inspiring better and better classical algorithms. So yeah, thank you so much for sharing the work with us.
Well, my pleasure. Thank you very much again for inviting me.
Yeah, thank you.